All right, so let's move on tonight. Let's talk about model-driven test design. So we have a fundamental problem in software testing. And the fundamental problem is that there's no other engineering discipline that builds things even nearly as complicated as software. And if you consider, one of the most complicated pieces of engineering around, I would argue, and you might have other favorite examples, but I'm an airplane guy, so I always go there first. An airliner is probably one of the most complex pieces of mechanical engineering around, and it has tens of thousands of pieces held together by probably hundreds of thousands of fasteners of various types. But when you look at a fairly sizable piece of code, you may quite easily find code bases that are 5 million, 10 million, 20 million lines of code with millions of decision points. And so all of those decision points you would kind of equate to moving parts, right? So an airliner might have a million parts, but it might only have several thousand moving parts. And software can easily have, the equivalent of millions of moving parts. So it's incredibly complicated. And when we start to talk about correctness, correctness really isn't that meaningful a term. I mean, could you ask whether a building is correct or whether a car is correct? Well, the better question is, are they fit for purpose, right? Can they be used at reasonable risk? Are they fit for purpose? There's certainly never been a perfect building or a perfect car or a perfect any other engineering artifact that's been built. They can all break, they can all fail in various ways. Some are better than others. But trying to strive for correctness in software, especially given that it's so much more complicated than things in other engineering disciplines, is kind of unachievable, right? It's really not something we can seriously contemplate. So just like other engineering disciplines, we have to use some senses of abstraction to manage the complexity. And so what we need to do is we need to build models that abstract the complexity of the software so that we can then start to build testing and to approach our testing from the perspective of the model instead of from the perspective necessarily of every line of code. We also need to keep in mind that testing can only show the presence of failures. Testing cannot show the absence of failures. The more thoroughly we test and continue to not find failures, that gives us a pretty good sense that we are reducing risk, right? We're setting a lower and lower upper limit on the number of failures that our system may have. Okay, I tried that and there's no failure there. I tried that and there's no failure there. So we're burning down that risk, but we can never get to zero because in almost any piece of real software, and frankly, in almost any piece of toy software, the total number of tests that you could possibly do are essentially infinitely large. So a couple more terms we'll put out there. What is testing? Testing is the evaluation of software by observing its execution. What is a test failure? A test failure is execution of a test that results in a software failure. So we run the test reaches a fault, the fault induces an error, the error propagates to the point where we can observe it as a failure, the test fails. And then debugging, while I said that we weren't really going to use the term bug, nevertheless the term debugging kind of slips in, and the action of debugging is just the process of, given a failure, how do I go back and find the fault? And sometimes it's quite easy, and sometimes you spend hours in front of the debugger trying lots of different test cases and trying to understand what the sequence of events is that led to this, observable failure. And of course, as we've already seen, not all inputs will cause a fault to become a failure. Okay, if I just admitted you, I hope you weren't waiting too long. So, we want to use all these things to try to drive test behavior. And, my goal is, I've set myself an unachievable goal of a good comic a week. So we'll start off with this one with the Dilbert Pointy Hair Boss. Our goal is to write bug-free software. We're going to pay a $10 bonus for every bug you find and fix. Right, the predictable outcome. I hope this drives the right behavior. Probably not. All right, so let's take a little bit of a deeper dive now into our model of what faults, failures, and errors look like. We talked about those three terms last week, and we've kind of been nibbling around the edges of this, but we have the Ripper fault and failure model. And this is important. It's going to come up again and again during the semester. So we have 4 different conditions that are necessary for a failure in the software, or for a fault in the software. See, I do it too. A fault in the software to be observed as a failure. And the first condition is reachability. That's the R in Ripper, in case this wasn't going to be obvious. So the location or the locations in the program that contain the fault must be reached by a test, right? So the test, the thread of execution, has to actually execute that fault. The second condition in the Ripper model is infection. The state of the program must be incorrect, right? So executing the fault has to infect the internal state with some kind of error. Bad value in a variable, unexpected program execution, right? An unexpected program counter, something like that. We have to have that infection of program state. Following that bad program state, that infected program state, must propagate somewhere to an observable output. If it never comes out, right, if there's no way to observe it, then it can't be a failure, even though it's an error. So that error has to propagate somewhere to some output of the program somehow. And then last of all, the R in Ripper, or the last R in Ripper, revealability. Or as someone corrected me last semester, shouldn't that be revelation? But that's such a loaded term, I'm sticking with revealability. The tester must be able to observe part of the incorrect portion, right? The failure must be detected by a test. So what this says is that if I run a test and the test reaches a fault and the fault causes an error and that error propagates to an output, but I never look at the output, then there's no failure. Kind of like if a tree falls in the forest and no one's there to hear it, did it make a sound? Right? If I don't have a test that actually checks the output, then there's no failure. All right, so that is the Ripper model. So let's take a look a little bit graphically at what does that look like? So we've got some test, and the first condition is our test has to reach some fault in the software. That fault has to infect the program state with some incorrect state. And then that has to propagate somehow so that of the total program state, there has to be at least some portion of the total program state that's incorrect. And then we have a test oracle. And the test oracle is simply the part of the test that's checking the results, that's validating the results or verifying the results. So if my test oracle looks at some piece of program state, but that piece of program state is correct, then I have not detected the fault. And if I haven't detected the fault, there's no failure. If, on the other hand, I look at some other piece of program state and I can say, oh, hey, part of that program state that I'm checking is wrong. I have detected the fault. I have detected the error, is really what I should say. I've detected the error in the internal state, and now there's a failure. All right, so let's talk a little bit about testing levels. And I'm going to start with kind of the traditional view of testing levels. You know, and in that traditional view, we'll usually start with unit testing. We'll test each individual unit, each class, or maybe even each method in the class. We will test those individually and make sure that on their own in a standalone way, those each do what we expect. Yes? I'm sorry, was there a question? Okay. All right, so unit testing, we're testing at that lowest level. From there, we might go up to module testing. In module testing, we might be testing each class and testing the interaction of the modules within each class. We can then go to integration testing. How do these classes work together? Right now, I'm starting to put multiple classes together. I say classes, of course, when I say that I'm speaking in object-oriented terms. These terms aren't necessarily we're not really coupled, right? We don't have to be doing object-oriented development in order to use these levels of testing. That's just the example I've chosen. So we're looking at how multiple classes work together, how the main program calls each class. Then we'll go up another level and we'll start to look at system testing. Now I'm testing the system as a whole and I'm making sure that the functionality of the system is what I expect. And from last week's terminology, this would be verification, right? I'm checking to make sure that the entire system meets the requirements, meets, you know, whatever we decided this needs to do. And then as our last level, we might have acceptance testing. In acceptance testing, we're bringing in the users. Now by last week's terminology, we're talking about validation. We determined in system testing that the system behaves the way we expected it to behave, but now we're checking, does it actually do what the users need it to do? And so that leads us to this V model of software or systems development. This V model is kind of a holdover from, you know, from the antique days of waterfall development, which we have largely put behind us, yet it's still a pretty useful model of testing. And so if we were really doing waterfall development, which, you know, most people and most projects are not really doing anymore, but we would kind of sequentially go through this. We're going to do all the requirements, then we're going to do the architecture design, then the subsystem design, then the detail design, then the implementation, then we're going to unit test the implementation, then we're going to module test at the level of the detailed design, then we're going to integration test and system test and acceptance test, and now we're done. And we don't generally take that waterfall approach anymore because probably 99 times out of 100 and maybe 100 times out of 100, something happens along the way that causes us to go back. And if we planned the whole thing as one straightforward thing, assuming that nothing would ever go wrong, we almost invariably find ourselves replanning, backing up, stretching out the schedule, increasing the budget because we have unplanned work coming in. And really, we kind of knew all along that, you know, that was probably going to happen. Nevertheless, this is still a nice model of testing because it points out where you're getting the information from for each level of testing. So when you're doing unit testing, for example, your unit testing is primarily driven by the knowledge that you put into and got out of doing the implementation, right? That's the level of that you're working at. When I'm doing acceptance testing, I'm testing at the level of what my requirements were, or maybe even backed up a little further about what my use cases were, about what my user desires were. You know, how did we document what the users wanted to do? That's what we're going to test against in acceptance testing. So each one of these levels of testing kind of has its own matching level of abstraction that we're going to use to drive what we do during that testing phase. So let's talk a little about coverage criteria. We talked a little bit last week about coverage criteria and how basically when we're using coverage criteria, we're trying to make up a set of testing requirements that we can then satisfy. And when we've satisfied all of the testing requirements that we've set up for ourselves to match this criterion, then that enables us to say we're done. So even small programs, as I mentioned on a previous slide, right, too many inputs. So if we have this compute average, it takes in 3 integers and it spits back a double. That's, the average of those 3. Let's assume those integers are 32 bits each. There's 4 billion possible combinations for each. So that's almost 10 to the 29th possible tests. In essence, the entire input space is essentially infinite, right? I mean, there's no way we're going to be able to run 10 to the 29th tests. So we have to recognize right up front that even with simplistic programs like this one, we have way too much search space. There's no way to exhaustively test any significant piece of software. So what's our goal then? Our goal is then to try to go into this huge test space and try to find spots, right, individual test cases around that input space that will help us find the most problems. And we'd ideally like to do that with as few test cases as we can, and with each test case being, reasonably different from other test cases, right, to give us the best chance of finding the most problems. And so coverage criteria give us structured ways that we can use to search through the input space for good inputs while trying to maximize our search and trying to cut down the duplication or the overlap between tests. We want to have as few tests as we can in order to satisfy our risk reduction. And we want to have as little test duplication as possible. We want each test to count. So what does coverage criteria bring to us? It lets us maximize the bang for the buck, right? It lets us get the most valuable testing done for the least investment. It provides us traceability. So for each test, I might have traceability that says, oh, I chose this particular test because it shows that this requirement has been satisfied. Or I chose this particular test because it executes this line of code over here that no other test executed. I've got a reason, a traceable reason for each test. I've got a stopping function. I can have a reasonable idea of knowing when I'm done. If my testing criterion is, for example, statement coverage, right? I want to execute every statement in this piece of code. Well, I know how far along I am, more or less. It's a little more complicated than that. But when I've executed every piece of code, I know I'm done. I don't have to guess. I don't have to come up with more cases. I know I'm done. So that takes us to a couple more definitions. And the first is that of a test criterion. And a test criterion is some collection of rules and a process that defines what the test requirements are going to be. So a test criterion might be statement coverage, might be requirements coverage, might be function coverage, right? Call each function. Those test criterion will help us to produce test requirements. So if I have a test criterion that says execute every statement, then I have a set of test requirements where each statement is its own requirement. And I have to satisfy that requirement by executing the statement. Likewise, if my test criterion is verify every functional requirement, I go back to my requirements list. There's 100 things on my requirements list. Each test requirement might map to one of those functional requirements. So there are dozens, maybe hundreds of test criteria out there. However, they're based on they are all based on 4 basic approaches. either looking at the input space or the input domain and coming up with test cases by analyzing what the possible set of inputs is, by looking at graph models of something. We'll be talking mostly about graph models of source code, but source code isn't the only place that we can derive a graph model out of. We have test criteria that are based on analysis of logic expressions, and we can have test criteria that are based on analysis of program syntax. So these are the four basic, right, the four high-level categories that we can use to derive test criteria. And as we get a little further along in the course, you'll start to see that each lecture starts off with this graph with one of the boxes that we're going to be working with that week highlighted. So there's this old view. And I say old view, but I actually still use it, and I find it, I find it helpful in some ways, of testing as black box testing or white box testing. And in black box testing, we're treating the thing we're testing as a black box, meaning we don't see anything inside it, right? We don't know what its implementation is. We just have this thing. And so we're going to focus on external factors, like what are the possible inputs that I can stick into it? What are the requirements for it? What did the architecture look like? And I'm going to try to come up with test cases based on the things that surround the box. And the opposite of that is white box testing. I've also seen this called glass box or clear box testing. In white box testing, we can see inside the box, right? We can understand what the implementation is, and we can base our testing on that implementation. So if I want to think about this from, if I want to do an example of each, a minute ago, we looked at a function that took 3 integers and returned the average. If I were to do black box testing on that, I would think about what is the range of all of the inputs that I can put into it. And okay, it's clear that I can't pick every value, right? Every integer value and put every integer value in it, but I might be able to make some smart, some informed selection of test cases from the inputs and run those various input combinations through it and make sure that I get good results. For white box testing, I might simply open up the source file and say, okay, what happens? Okay, it adds these, it does a division, there's an if statement here. Now let me write some code that specifically tests all of these lines of code or tests all of these decision points somehow, right? So the big difference is, am I doing it based on the implementation, or am I doing it based on external factors, right? The environment that the thing lives in. Turns out the thing is that both of these are actually useful, because white box testing, where I'm writing tests based on the implementation, that's really good at finding errors of commission, right? It's really good at finding things I did wrong, but it's really bad at finding errors of omission. If I forgot, if there's some capability this should have and I didn't write that capability, there's no code in there for me to test. So I can test I can execute all the statements, I can execute all the branches, I can do whatever analysis of the code that I want. But if there's something missing from the code, I'll never get the right test. Black box testing is very good at finding those cases that are outside that. So the two are very complementary. So that said, if we start to look at model-driven test design, you can start to think that these distinctions are maybe less important, and there's a more general question. And the more general question is, what's the abstraction level that I'm using to come up with my tests? Am I using a very low abstraction level? I'm deriving tests based on the implementation. Well, that might be what we used to call white box testing. If I'm deriving the tests from an architecture analysis or a set of requirements, that's what we might call black box testing.
Hey, Bob,
Yeah.
Quick question.
Yep.
Is there something like gray box testing, like we can combine both the black and white and try to devise our own abstraction?
I've actually heard that term, It's not really a commonly used term. I don't know that there's any, when I say not commonly used, I think what I really mean is I don't know that there's any real definition for that, at least not that I'm familiar with. But as I said, combining those two is a really good approach to an overall kind of integrated testing plan. So, if you wanted to call that integrated testing plan gray box testing, I guess I would say you're welcome to do that.
Okay.
Hey, Bob, just a quick comment on that. Gray box testing, I haven't really heard as a phrase, but coming from like the program analysis community, is typically used like when you have some sort of ability to instrument the underlying bytecode or native, x86, what have you. So you don't have the source code, but you're able to instrument it with whatever, branch coverage or whatever.
I see what you're saying, right? So you're doing it based on a slightly different artifact, I guess.
Yeah, but I would agree it's a very like ambiguous term.
Yeah. Okay. Good. Thanks.
I have a question here. So if you remember earlier in one of the slides, we had the V model where we had the acceptance testing. So the black box testing is typically some kind of like acceptance, and then the other one, the white box testing, will be something like unit testing and module testing and integration testing.
Yeah, I think that's a fair statement. If you wanted to kind of map this V, or the test activities on the right side of this V, if you wanted to kind of map those into what's black box and what's white box, acceptance test and system testing, I'd say pretty clearly black box. Unit testing and module testing, pretty clearly white box. Although you can use black box techniques at those levels too, and some of the things that we'll do this semester, like input domain modeling, we're doing unit testing, but we're doing it based on, based on concerns from outside, based on possible inputs. So while I'd say this tends to be white box testing, it can also be black box testing. And then integration test. You could certainly use elements of both. I think that probably your tests will be more driven by black box concerns, and your debugging effort, if you're finding failures, will probably pretty quickly result, dive down into white box analysis.
Professor, real quick, I'm curious about black box testing and white box testing. Is there an effectiveness if you use a team who's familiar with code who's not familiar with the code for like something like black box testing? Because if they're familiar with the code, is there like a way that they might, because they know what's in it already, they might become it affect their at least test creation process? Yeah,
and I think you're right. When you're familiar with the code, you've got your own bias, right? You've got a built-in bias about what you're going to test. You're thinking about, as you're putting your tests together, you're thinking about the way you wrote it and what you think it should do, and that pretty strongly can influence what you're testing. So there is an argument, and it's not just an argument, it's a whole activity. IV&V, independent verification and validation, is basically having people that weren't involved in the implementation develop and execute the testing. Now, I'll also say that as you come to understand some of the test criteria that we're going to be talking about, the coverage criteria that we're going to be talking about this semester, you become increasingly able to say, okay, well, I know how this is built, but I also understand the criteria that I'm using to do this testing. I'm going to follow the criteria. That's going to force me to go outside of my comfort zone. It's going to force me to think about the software in ways that I hadn't really thought about the software before. So you can kind of rescue yourself, even if you're the one doing the implementation and the testing. You can use these coverage criteria to put you in a position where you're a lot less subject to those biases that you have built in because you're the one who wrote it. All right, so let's talk about some different testing activities. And we can break up our whole testing thing into 4 general types of activities, and we could maybe lump some together, or we could subdivide some, but we'll go with these 4. And the first one is test design. We have to be able to come up with some tests. And there's 2 ways we can do that, right? We can do that by a criteria-based approach or by a human-based approach. I'll talk about both of these. Then we have the test automation step, where we're taking those test designs and we're building them into something that can be executed, and preferably executed on an automated basis. Then we have the test execution itself, which is the running of the tests and the collecting of the test results. And then we have the test evaluation, which is analyzing those results to figure out whether the test was successful, which seems really easy, but in practice can actually be quite hard. And an interesting point here is that while often the same people are tasked, the same people or the same person is tasked to do all of these are actually very different activities that require a very different skill set. So if we look at criteria-based test design, here we're going to be designing our test values to satisfy coverage criteria. This is a very technical job in software testing, right? This requires a lot of analysis, may require some discrete math, certainly requires test theory, may require set theory, some other things like that. This is arguably, I hesitate to say what you should find intellectually stimulating and challenging, but generally speaking, this is a really interesting technical challenge. And if you don't have people who are qualified and trained to do test design, you're almost surely going to get some fairly poor tests. And this is what we're going to be spending once we get through the intro third of the semester, the remaining 2/3. Once we start buckling down on test criteria, coverage criteria, this is primarily what we're going to be doing this semester. We can also build human-based test designs. And here we're going to be coming up with test values based on our domain knowledge about what the thing is that we're testing. So, you might be asked to write, let me come up with a good example that isn't too far up my particular alley. You or your company might be hired to write a supermarket checkout point of sale system. And you can come up with all the tests you want. But it would also be really valuable to involve some supermarket managers and some supermarket cashiers in on the testing so that they can say, well, what really happens when I use this is this, right? I scan it and sometimes it doesn't scan, right? They're going to have domain knowledge that you as a software developer probably don't have. I mean, unless you spend your career in grocery store checkout systems, in which case you build your domain knowledge in it and you become an expert over time. But a lot of the time, we're kind of hopping from project to project or from job to job, and we don't always have that deep domain knowledge that some other expert has. And so this is actually a lot harder than it seems to us. We start off going, oh yeah, I can handle that. And then you put it out there and there's all kinds of problems because there's all kinds of domain related things you didn't think of, and you slowly learn that that's actually a lot harder than it seems like. It also solves the problem that criteria-based approaches, they're not very good at finding those special cases. And special cases might be very, very obvious to someone who's versed in the domain. I'm having a hard time coming up with a grocery store special case example, but I think you can probably imagine, if I'm building my tests based on covering all the code, well, that doesn't necessarily cover any special cases that might execute the code in a particular order or whatever, right? So this gives us some additional insight. Doesn't really require traditional computer science. Often, might not even require a lot of engineering knowledge, but you have to have a good background in the area. So this can be interesting too, not typically to us as software developers, because we often don't have the background in that area, and we often don't really want to become experts in that area, because if we did, we'd have selected a career in grocery checkout. Joking a little, but all right, so then we have test automation. So in test automation, we're going to take those test values, those tests that were designed in the previous phase, and we're going to turn them into something executable. So it's a little less technical. It's a little more turn the crank, right? It requires knowledge of programming. I have to be able to write JUnit tests or Python tests or Cucumber tests, right? So I have to have some technical knowledge, but I don't need to know about test criteria, right? I'm just implementing these tests that have already come out. For for highly skilled test designers, this can be kind of dull. On the other hand, it's often outside the skill set of the users and the domain experts. So my grocery store manager who's been helping me with the test design, it's unlikely I might think, as the test theory expert, oh, writing those JUnit tests, that's going to be boring. I'm going to give it to the grocery store manager. That's actually probably not a good choice either, right? Maybe I need some third group of people who are, skilled test implementers, but maybe aren't at the level of knowledge that would make them good test designers. Then we have test execution. We want to run the tests on the software and collect the results. And if we've done a good job automating our tests, then it's relatively easy to run the tests and collect the results. This tends to be something that test designers and software developers in general find boring to do, and I can't say that I blame them. Repeatedly running tests, that's really just not a lot of fun. Especially if the tests are not automated, because then it can require a whole lot of labor. I worked on a fairly large airborne system some years ago, and we had a set of manual tests that took about 2 to 3 weeks to get through. And we had a really good test engineer who would spend her days down in the lab running the tests on this system. She took extraordinarily good notes. She knew exactly what worked, exactly what didn't work. I could have never done that. I'd have gone crazy. She was great at it. Last of all, we've got test evaluation. We've collected the results. Now we have to analyze them and report back to the developers and say, here's what happened. That seems easy, and sometimes it is. If you're writing JUnit tests and saying, okay, I'm going to average 2, 2, and 2, and the answer should be 2. I'm going to average 1, 3, and 5, and the answer should be 3. Note that I'm only picking ones that's easy for me to do in my head. Okay, it's easy to evaluate those tests. But as you get up to higher levels of automated testing and you're trying to automate your integration test or automate your system test, imagine I'll pick a weather radar. We take a weather radar, we feed a bunch of data into it, and it comes out with this pattern of, reds and greens on the screen. Is that right? Wow, okay, that's actually a really hard question. There's a lot of processing that went on to represent in some abstract form what the very specific input was that went into it. How do we determine that that's exactly right? And if I run it multiple times and I get slightly different pictures, which is not impossible, how do I determine when a slightly different picture is okay versus when a slightly different picture is broken? Right, so this can actually be really hard. Then there are some other testing activities that we don't really get into here in this class. We've got test management, right? If we're going to run a bunch of tests, we have to have a policy. Here's how we work. Here's the teams we organize. Here's how the test team gets along with the development team. Here's how we report success or failure or schedules or budget or whatever to the management team. We've got test maintenance activities. I think you're starting to get the hint here that testing is a lot of work. We're going to spend a lot of time doing test development, doing test implementation. Once we've done that, what are we going to do? Well, it seems like it would be a bad idea to just say, okay, we're done testing and throw the tests away, especially with a long-lived system that we're going to continue to maintain over time. We want to keep those tests so that we can keep getting value out of them. We spent a lot of money and a lot of time on them. Let's get as much value out of them as we can. But that requires maintenance, just like any other piece of code requires maintenance. Last of all, we've got test documentation. We have to be able to explain the reason behind each test. We have to be able to explain what each test is doing. We have to be able to trace each test back to the underlying reason why that test exists in the first place. All right, so using model-driven test design in practice, by breaking it up this way, we're trying to give the opportunity, just like traditional engineering does, to put the right people on the right parts of the effort. Right, we've got different skill sets that are needed to find the test values, automate them, run them, and evaluate them. Just like in traditional engineering, we've got an engineer who is going to, do some mathematical analysis and come up with a design, and then there's going to be well, I mean, there used to be a draftsman or draftswoman who would draw it up. Now that's not usually the case anymore. But somebody's going to have to build it. Somebody's going to have to cut the metal. Somebody's going to weld it together, right? There's all kinds of levels of things that have to happen to produce that entire engineering project. And the key thing that you have here is that the test designers, by their very nature, are becoming technical experts on the entire system, because they have to have an in-depth understanding of the system and of the testing approaches in order to be successful. So we've kind of elevated the testers, from the old days where the developers write something, they say, I'm done, it all works. They throw it over the wall to the testers, and then the testers try to break it. In that scenario, the testers are kind of second-class citizens, right? They get it last. If the ship deadline is coming up, whose time gets cut? The tester's time gets cut. Here we're kind of changing the model around, and we're kind of putting test designers in part of the, as part of the technical leadership team of the whole effort. All right, so let's look at this graphically. MDDT, model-driven test design. Defining MDTD won't be on a quiz. It's okay. So let's look at the steps that we have here. So we're going to start with some software artifact. And I've got two different levels here. I've got the implementation abstraction level. I've got the design abstraction level. You might want to think about these as white box on the bottom, black box on the top. I'm not sure it's going to map exactly correctly that way, but it's a close approximation. So we've got some software artifact. First thing we need to do is to do some analysis of that software artifact and create some kind of model of that software artifact. Can we create a control flow graph? Can we create a state chart? What kind of model can we create? Then we're going to take that model, we're going to apply some test criterion to it. So for example, we might create a state chart, right? A finite state machine as a model of the software artifact. And then we can start to say, oh, my criterion here should be to cover every transition of the finite state machine. That leads us to a set of test requirements, where each test requirement is the execution of one transition of the finite state machine model. We might also do a human-based domain analysis, right? Get a domain expert in to say, oh, what worries me is when the cashier double scans something, how does the system know the difference between you bought 2 of them versus it rang up twice, right? And that would bring in some domain expertise and start to give us test requirements. Okay, so if it double scans within 100 milliseconds, maybe it should count as 1, but if it's more than that, it should count as 2. I don't know, I'm making this up, but we have some human-based test requirements that come out of it. We're going to combine those together, we're going to refine them, we're going to create some refined test specifications. We're going to use those test specifications to generate input values. So now we've taken the test requirements, which are kind of abstract. The test requirements are cover this state transition. The input values may be everything that's needed to get us into that state and then to drive us across that state transition. That's right, we're getting much more concrete now. We're back into the implementation level. And then we're going to find out, okay, what do I need to do, prefix, postfix, and expected? What do I need to do to set the system up into the right state so that I can execute these input values? What do I need to do to clean up after I've executed these input values? And what is the expected value? What is the expected result, and how will I measure and collect it? Then we're going to automate that and build some test scripts, maybe JUnit, maybe something else, but JUnit's a good example, right? We're going to take that knowledge that we had, we're going to encode it in something that's executable. Then we're going to execute it and collect our test results. And then we're going to evaluate those test results and decide whether we've passed or failed. So that's kind of the whole around the block pass at how do we get from a software artifact to a set of passing and failing tests. Now we can abstract this up a little more and kind of combine a few pieces together to get back to those 4 categories that we talked about. And so if we do that, we've really got test design, which is doing the modeling of the software, or the the human-based domain analysis, coming up with the test requirements, turning those test requirements into specifications. Then we've got the test automation effort, taking those test specifications, deciding what the specific input values will be, and building them out into test scripts. And then we have test execution and test evaluation. So now we've kind of mapped back to the 4 steps that we had on the previous slides. And so by kind of taking this up a level, right, we're going to raise the abstraction level of how we're dealing with our software or our system that we're testing. And that just kind of makes the whole test design process just a little easier to get our hands around. We've got a limited number of tasks that we need to do. We can group them together into the domain of a limited number of people. And then in this class, as I mentioned before, really we're going to be concentrating most of the class on the test design phase. We're going to be looking at building models and extracting structure. We're going to be looking at applying criteria to get test requirements. We're going to be looking at, to some extent, how to take those test requirements and create input values from them. That's going to be largely the lecture content and the class exercise content. And then to some extent, the homework assignment content is going to be the rest of this, right? To say, okay, how do I do that and then also do some implementation of it, just so that you get a little bit more experience and a little more feel for the whole process. All right, so a quick example. Here we've got this, this Java program. This is a, what is this? This is a member, okay, this is a member function. Or a class method inside a class. The class has this thing called list. List is some kind of collection of items. We don't really know what. We don't really care what. And we want to pass in an object, and we want this index of function to either return us the position in the list where this object exists, or a -1 if the object doesn't exist. So one thing we could do here would be to create a control flow graph. So we can look at the control flow graph here, and now hopefully you've all got some familiarity with control flow graphs and how to extract them out of source code. But basically we've taken the source code and we've built it up into these nodes. So when our source code runs, we set I is equal to 0, then we check whether I is less than the list size. If it is less than the list size, we come down this side to number 4. Here's our if statement, if the list.get blah, blah, blah. If that's true, we return I. If it's false, we increment I and we go back and check the list again. And if we get to the end of the list without finding anything, then we bail out from 2 to 3 and we return -1. So there's our control flow graph of this function. Given that control flow graph, we can, for example, we can note we've got an initial node an initial node, node number 1. We've got 2 final nodes, node 3 and node 5. So any test that we write is going to have to start at the initial node. It's going to have to end at a final node. And then we can identify, for example, a potential test criteria is identify all of the edges and say, well, we want to execute all the edges in this graph. So I want to execute edge 1, 2, and 2, 3, and 2, 4, and 4, 5, 4, 6, 6, 2. Those are all the possible edges in the graph. And we've got some nice tools for this. So if you check this site out, this is the book website. Be sure to check this out because there's a couple of tools there that give some really nice support for graph analysis and for logic analysis and for some of the other things we're going to do. And you are completely okay to use those tools as part of quizzes and the final exam. That's part of the open book thing. So be sure to check that out. So we could come up with some test requirements, right? And so we've got 6 requirements for edge coverage. For each edge, there is 1 requirement. Cover that edge, right? Execute that edge. We could come up with some test paths to do that. And a test path is just a sequence of execution through this graph that'll get us there. So we need 2 test paths. We need 1, 2, 3. And we need 1, 2, 4, 6, 2, 4, 5. There are other combinations of test paths that could do it too. These are not the only possible test paths, but these are 2 test paths that together cover all of the edges. So now we need to find some test values that will execute these test paths. So now we have to go back and we have to simultaneously think about the graph and the code, and it's hard to show it all at the same time. But if I want to execute test path 1, 2, 3, what could I do? Well, I could set my list to the null list, or the empty list, and then I could pass in anything as my object. And here I'll just use null because it's easy enough. And if my list is empty, then I'll come in here, I'll set I to 1. I'll say, is I less than list.size? No, list.size is 0. So we'll exit here, we'll come over to node 3, and we'll return 0, or we'll return -1. So these inputs satisfy that test path, or will cause that test path to be executed. What about 1, 2, 4, 6, 2, 4, 5? All right, that's a little more complicated. We need to go around the list at least once. We need to go around the list around the loop exactly once. So what if I set my list to 1 and 2 and I ask it to find 2? It'll come in, it'll set I to 0, it'll say, is I less than list.size? Yes, it is, good. It'll say, is the first element in the list 2? Nope, okay, let's increment I, we'll go back around. Is I still less than the size of the list? Yes, it is. Is 2 the current element of the list? Yes. And so we'll come over to 5 and bail out. So that set of inputs will execute that test path. And we'll talk a lot more about test implementation and finding values that execute paths in some future classes. All right, so that is it for our lecture time. I'm a little over where I want to be, but let's go ahead and let's take a break until 6:25, and we'll come back at 6:25. Get you broken up into your groups, and we'll do some exercises based on this. All right, so see you in 11 minutes.